All right, thanks, Mark. So today's speaker is Deborah Sulsky. She's a professor at the Department of Mathematics and Statistics at the University of New Mexico. Her research interests have included over the years biomathematics, continuum mechanics, and scientific computation. And she's developed numerical algorithms for studying problems in embryology, population ecology, suspension flow, fluid mechanics, and solid mechanics. She's currently the PI of a recently funded SIDAC-5 E3SM ecosystem project that is whose aim is to put the material point method and elastic decohesive rheology into MPAS-SI. Great. Go ahead, Deborah.
Thank you, Adrian. I think that summarizes the talk. So thank you to everyone for coming. Going to give an overview of this ecosystem project, which we call MPAS-SI-MPM, and tell you what our plans and goals are. So first, let me just acknowledge all of the participants in the project. There's 3 universities: University of New Mexico, University of Nebraska at Lincoln, and RPI, and participants from Los Alamos and Sandia Labs. At UNM, as you know, I'm the PI on the project. Howard Schreier is a mechanical engineer, expert in constitutive modeling, and he's consulting on the project. And Han Tran also has a background in mechanics and scientific computing. Yaowen Guan is a statistician with expertise on parameter calibration and model validation. And RPI participants from FastMath have expertise in GPU acceleration. And Adrian and Andrew, I'm sure you all know, are CICE experts and mechanics and computational people, similarly for Kara, Devin, and Svetoslav. So as Adrian said, our project is to enhance the representation of CICE mechanics and hopefully more accurately capture the deformation, in particular the formation of leads, which are areas of open water caused by fractures in the ice cover, with the idea that by modeling the ice mechanics, especially the local deformation, more accurately, we can improve the predicted fluxes between the various components of E3SM. And I just want to mention that leads, the fractures occupy a very small area, and so they're very localized deformation, but account for a large fraction of the heat flux, for example, and also responsible for localized formation of dense water is another example of these local interactions. The way that we include leads in the simulation is through the constitutive model called the elastic decohesive model. And I'll talk a little bit more about that in a later slide. But the main idea, the elastic part, is that intact ice is modeled as an elastic solid, and the decohesive part models fractures in the ice to form the areas of open water. And the model also includes closing and refreezing of the leads. Also part of this project is to develop techniques for parameter calibration for this model, especially in the presence of leads, which are represent discontinuities in the displacement field. And so new methods are required there. And another important objective is to move the CICE dynamics to GPUs. And we'll be using the PumiPic library developed at FastMath for this purpose. So the approach to accomplishing those objectives has 4 parts. There's obviously model development and its implementation. And to implement the model, we're going to use the material point method. We've already mentioned the elastic decohesive constitutive model for the modeling the fractures. And this is going to be implemented on MPAS meshes for CPUs and GPUs. The material point method is a method that's been around for about 30 years now. It's a general method for solving continuum mechanics problems. And it's been used for sea ice. I've used it for sea ice, but not on MPAS meshes, and using quadrilaterals, and it's been used with triangular meshes and things like that. So the implementation on polygonal meshes on the sphere is new to this project. Another important aspect of our project is the validation and verification. We've designed a suite of test problems and milestone simulations over the course of the project. But in order to tell how well we're doing, we need to develop good metrics for model performance, both to compare between different models and also to compare with observations, in order to know whether we're having any impact on our ultimate goal of improving the climate simulations. And in particular, the metrics are needed for leads, as I said, where these are discontinuities in the displacement field. And I'll show a little bit more about that later. The model calibration, the new contributions there are going to be related to using, well, both standard metrics, but the new metrics that we're developing, and be able to calibrate the parameters in the model. We assume changing the constitutive model will necessitate potentially tweaking some of the default parameters in other parts of the simulation. And obviously, we want to demonstrate these capabilities in the end, and we're targeting a 50-year fully coupled climate simulation. So I'll go through why we decided on these various aspects of the modeling that we're proposing. So for the elastic decohesive model, as I mentioned, it has an explicit representation of leads and sea ice. The picture on the lower left, I don't know if you can see the cursor, but the lower left is a picture of sea ice with showing a lead, a fracture in the ice. And we represent that as a jump in displacement, with here written mathematically with components normal and tangential to the direction of the lead. And the elastic decohesive model was developed so that we have a function of stress that tells us the stress state at which a fracture starts. And so that's tells us the initiation of a lead and its orientation. And then the decohesive part of the model represents the fact that the fracture doesn't occur instantaneously. The complete fracture occurs over a small distance as the jump in displacement develops. And over that small distance, we reduce the forces on the surface, because a free surface, a fracture, has no traction on the surface. So that's a rough idea of the elastic decohesive model. Why do we want to include leads? Well, in the winter, when the sea ice, when the ocean water starts to freeze up, if it were static, for example, it would freeze to a thickness of a couple of meters. So that because the ice insulates the ocean from the atmosphere. And when fractures form, you're exposing the warmer ocean water to the cold atmosphere. You get rapid freezing of ice. If the ocean and wind currents change direction, the ice that forms in those leads can be piled up. On the right here, you can see ridges or forced down into keels. And so this is a mechanism that can provide more ice per unit area than you would expect from just the static equilibrium conditions. So it affects the Arctic landscape and force balance, changes drag laws and things like that. So these localized deformations are an important aspect of the ice physics. This is an example. I mentioned that we have implemented MPM with the elastic decohesive model. This is on a cube-sphered grid, so it's essentially a quadrilateral mesh. This is showing the Arctic, and this is a movie over the year 2003 on the left. So this is a MIT GCM implementation of an ocean and ice model, and we're using reanalysis data for the atmospheric forcing. And on the left is a implementation of the elastic viscous plastic model, and on the right is the elastic decohesive model. The color is ice concentration. You can see, particularly in the summer, you can see what fractures forming. Let it run around again. Here in the summer, you can see quite a bit of the fracturing more explicitly. But there are fractures occurring even when the ice is more concentrated. So this was some preliminary calculations that motivated us to suggest putting this into E3SM. And this is a similar comparison, except on the right is elastic decohesive model, and on the left is ice concentration as measured by Nimbus 7 satellite observations. So the blue hole is around the North Pole where there are no measurements. You can see similar ice concentration between the observations and the simulation. Okay, why did we decide that we want MPM in the modeling effort? The material point method provides a dual description of the material. It's a set of points that are followed, the trajectories are followed, so that's a Lagrangian description of the material. And then we also use the MPAS mesh, so that you can think of that as an Eulerian description of the material. And the material points have all the ice state variables and dynamics variables. And one advantage of MPM is that advection is performed by moving the material points, and they carry their state with them. So there's no diffusion associated with moving state variables. And that includes all of the column physics variables in sea ice and the biogeochemistry, for example. However, in a Lagrangian description where you have isolated points, it's hard to compute derivatives. You have to find nearest neighbors and do comparisons. And so with MPM, what we do is project information from the material points onto the grid. We call that function reconstruction. So if we think of the material points as carrying function values on an irregular grid, we reconstruct functions to whatever order accuracy we want at either nodes or cell centers, depending on where you want the data for the mesh solution. Then solve a momentum equation on the mesh, and then use the flow computed on the mesh to update the material points. So the points move in that flow, and one of the little subtleties of MPM is that when we map information from the mesh back to the material points, we only map the changes in the values, not the values themselves. And so this the dissipation that can be introduced by mapping quantities back and forth is minimized by doing that. But another important aspect of the Lagrangian description is that it's useful for constitutive models with history dependence, where you need to know information about the deformation along the trajectory of a point. And that's helpful for the elastic decohesive model. Um, in the first few months of the project, we have almost a working implementation of MPM on the spherical MPAS mesh. On the left here is uh, just a depiction of an initialization of the ice in the Arctic and Antarctic using material points. These are colored by ice concentration, which in this example was uniformly 1, so they have a uniform color. But that's the initialization. And this is a dynamic test that I'm illustrating on the right, just showing advection with material points. So on the top row here, there's actually 2 configurations. The first 2 show a cosine bell distribution of ice concentration, just 2 different views. And then the third one is a slotted cylinder with a constant ice concentration. And so this is the initial configuration. They're jagged because right now we're initializing the material points from the grid representation of these quantities rather than from a exact geometric description, but we can fix the jaggedness. We prescribe a velocity, a constant velocity of this form, U naught cosine phi, where phi is the latitude, and U naught is 2 pi r, r the radius of the Earth, divided by 120 days. So when we run this simulation for 120 days, the material point configuration, the final configuration and the initial configuration should be identical. And so here I'm showing the final configuration and the initial configuration. The final configuration is the filled dots, and the initial configuration are open red circles, and you can see that we get essentially the exact answer because this is a constant velocity field. And similarly here for the slotted cylinder. So this jagged initial configuration is exactly reproduced in the final configuration. If we had a more complicated velocity field, we wouldn't get the exact answer. We do function reconstruction to second order, which means that we reproduce constants and linear fields exactly. But anything other than that, then there would be discretization errors up to the order of the method, and we're aiming for second order accuracy in the entire algorithm. PumiPic, I mentioned is how we're going to do GPU acceleration. So PumiPic is a library that was developed at FastMath for doing particle and cell calculations in fusion reactors. And MPM is derived from particle and cell method, and so this is a good fit for building on the PumiPic library. The performance has been demonstrated, I guess, on the Summit system most, but it's been implemented on Frontier and Perlmutter. And for the MPAS-SI, some changes have to be made to deal with the Voronoi meshes and the spherical geometry. And that library is being called PolyMPO at the current time, and it's built on top of PumiPic to support the operations that we need in this project. And so the moving least squares function reconstruction that we're doing on MPAS meshes, the mesh to material point interpolation using Walk-Sparse basis functions, material point relocation. What that means is that when the points move, we need to know which cell they're in, and so identifying that is also going to be on the GPUs. And this library has these basic operations already implemented. The current finishing touches are being made on the Fortran interface using ISO-C bindings, and so we expect relatively soon to be running on GPUs. This is just an example of a PUMI-PIC simulation in the fusion reaction, showing the complicated meshes that they use. So this is a code called Guitar M. It's just particle tracking, so just tracer particles tracing impurities in the reaction. The impurities tend to form on surfaces and then move into the interior of the tokamak. But you can see complicated geometry, local refined areas. These are probes, highly unstructured mesh, and hundreds of millions of particles, and getting good performance from that library. And I mentioned also that, switching topics now, that we need new metrics. So let me give you an example motivating that. This is just a cartoon. Suppose that these are observation or simulation, or two different simulations of fractures. It's unreasonable to assume that we're going to predict exactly where a fracture in the ice occurs compared to an observation, and we're not going to get the exact shape. But we feel like if we get roughly the right number of fractures, so good distribution, and roughly the right orientation of these fractures in approximately the right place, that we'll be getting the fluxes accurate for climate simulations. So the question remains, though, how do we tell then whether we're doing well or not? And if you just take an L2 difference, a Euclidean norm difference between these two images, you can have very large errors if the two discontinuities are slightly displaced from one another or misshapen. And so an idea that we've been working on is a metric based on what we call image warping, which is just a diffeomorphism between these two domains. So can we map one image onto the other, and then the metrics that we use for determining errors is based on the size of the warp, the size of the diffeomorphism, a norm on that, plus the difference after the warp. And in a 1D example of a function here, we might have a red curve and a green curve, and if we try an L2 difference, you have large error because they're displaced from one another. But after warping, we can measure the difference, and you can think of the size of the warp as sort of a phase error, and then the difference afterwards as being an amplitude error. And so that's what we're currently looking at as a metric for measuring differences. And here's an example. This is a small calculation on the Beaufort Sea. The orange part on the left of these figures is the north coast of Alaska, so north is to the right. The first image is some processing that we've done of RadarSat data to try to show where leads are, where the fractures are. So the color is the magnitude of the jump in displacement. The center picture was an MPM calculation showing our best guess of the result from parameters using our best guess. And then on the right, this is a first attempt to do some calibration just of the ice strength parameters, just two parameters in the model, using this image warping idea. And so you can see that it cleaned up this area a little bit here, but maybe we lost some of the smaller fractures. And so we're still looking at perfecting some of these ideas, but it looks promising. So to conclude, I wanted to just go over what impact we hope to have. Again, we hope to improve the physical description of sea ice in E3SM using the elastic decohesive model, and that this will give us better representation of some small-scale sea ice deformation features and the coupling fluxes that are generated by those. We will be utilizing GPU accelerators for the sea ice component, and so hopefully that moves the sea ice to GPUs. and we get appropriate speed up. And also, we expect to be developing metrics that we think can be useful for analyzing spatiotemporal, not just sea ice data, but spatiotemporal data in general, leads in particular, and that these metrics can be useful in other components of the model as well. And I just will put up a slide with some references in case people are interested in some more of the background information. And with that, I'll stop and happily answer any questions.
Great. Thank you, Deborah.